Hello everybody and welcome to paper of the day. Today I'm going to present the paper PARAMANU, Compact and Competitive Monolingual Language Models for Low Resource Morphologically Rich Indian Languages. The title is quite long, but the paper is interesting. So this paper was presented in ACL 2026 and without further ado, let's dive into it. So first off, what are the motivations and the objectives of that paper? So the main motivation comes from the fact that current NLP systems remain strangely biased towards English and other high resource languages. This is particularly problematic for Indian languages, which are spoken by a very large population but remains relatively underrepresented in training data. The authors identify several problems with multilingual models, English-centric training, imbalance between languages, and especially tokenizer over segmentations. This last point is important because Indian languages can be morphologically rich, meaning that words contain several meaningful components. A general tokenizer can therefore break them into too many tokens, increasing both computational cost and potentially hurting the representation of the language. So the objective of Paramanu is consequently to ask whether we can build smaller language-specific models that are better adapted to those characteristics while remaining affordable to train. So um, now let's talk about the training. Okay, so the authors here choose not to adapt an existing English-centric LLM, instead to train the models from scratch using language-specific data. The five main models correspond to Bangla, Hindi, Marathi, Tamil, and Telugu, which sizes between 108 and 367 million parameter. The total pre-training corpus contains 45.6 gigabytes of clean text. An important aspect of the paper is the very limited computational budget. The models are trained on a single A100 GPU with a budget below $1,000. So the philosophy of the paper is not to compete through scale, but through specialization and efficiency. So now let's talk a bit more about the methodology. So the paper introduces two particularly interesting technical components. So the first one is the hybrid tokenizer, which combines BPE and Unigram LM. So the idea is to preserve meaningful morphological units instead of breaking words into unnecessarily small pieces. This is illustrated in the figure 1, compared with Sarvam, Llama, Gemma, and GPT-4o, the Paramanu tokenizer achieved the lowest fertility across the evaluated languages. In other words, it needs fewer tokens to represent the same texts. And if we look at the second component, which is the rope positional interpolation, which is shown in the figure number 2, the authors want to train with longer sequences than their hardware will normally allow. They therefore scale the position indices before applying rope mapping. Before applying rope, which will map the long sequence into a smaller hardware supported range. So this allows them to experiment with longer context while keeping the same hardware configuration. Now onto the main results. We can look at the main result in the table too. So I know it's a bit small, so don't hesitate to zoom in. So the main observation is that the instruction-tuned Paramanu models outperform the models below 3 billion parameters, and in almost all cases. So the main exception is that Sarvam 2B, which performs slightly better on Tamil and Telugu, but the scale of the training is very different. Sarvam 2B was trained on around 4 trillion tokens, whereas Paramanu uses a much smaller training budget. More surprisingly here, Paramanu also outperforms larger models such as OpenHati 7 billion and Heravata 7 billion in the evaluated settings and remains competitive with several other models above 3 billion parameters. Of course, the largest models, especially Llama 3, 8 billion, and Bloom's 7 billion, still achieve the strongest overall results. So the authors are not claiming that small models are universally better. Their main claim is about the performance to cost trade-off. Now, why does Paramanu works? Here, the authors investigate why these relatively small models perform so well. And first, in the table 3, they evaluate the tokenizer and the data cleaning. So adding the unigram components improved performance across all 5 languages. The gains range from 0.56% for Tamil to 2.02% for Telugu. Data cleaning also has a significant impact. For example, removing the cleaning steps decreases performance by around 3.5% for Marathi and 2% for Telugu. Table 4 here then looks at the context scaling. Increasing the context from 256 to 1024 tokens generally improves performance, although Telugu behaves less consistently. Finally, instruction tuning provides important gains, particularly for Hindi, where performance increases by around 9%, and Bangla, where the gain is around 4.3%. So overall, the results suggest that the performance comes from the combination of several relatively small but carefully designed choices. So finally, what can we take from all of that? So the paper makes several important contributions. First off, it provides a family of open source Indian language models below 400 million parameters, together with their tokenizers and their datasets. Second, the experiments show that careful language-specific design can compensate for a large difference in model size. Tokenization, data cleaning, and instruction tuning all have measurable effects. The paper also finds interesting cross-lingual transfer. So in the table 5, for example, that I did not implement it, but the table 5 showed that Marathi model performs strongly on Hindi, and even the Sanskrit model can achieve a strong Hindi score despite not being trained on Hindi. And however, we have some important limitations. So for example, the training corpus is still relatively limited, instruction data relies partly on machine translation, and the models were trained with very restricted compute. For future work, the author proposed extending this approach to other morphologically rich and agglutinative languages while improving the data and scaling the methodology. Overall, the key message I take from this paper is that for low resource languages, increasing model size is not necessarily the only way to improve performance. Careful language specific design can provide a much more efficient alternative. Thank you for listening.